At this point, you should probably be questioning this assumption that the conditional variance is going to be equal to the conditional mean for all values of increasing x, right? And although it does look, just by eyeballing it from a bivariate scatter plot, that this assumption might hold, we actually do have a way that we can more formally check to see if there's any over-dispersion. And by over-dispersion, I mean that the conditional variance is not equal to the conditional mean. So there's several tests that we can use, including a likelihood ratio test, to see if there's any over-dispersion of that lambda parameter by running the same model using a negative binomial distribution. Now, we can also do this much more easily just by using the AER package that includes the function called dispersion test to test for over-dispersion. And one common cause of over-dispersion is going to be an excess of zeros, which in turn is probably generated by some other data generating process. And we'll come back to this in a second, because then there's a different type of model called a zero-inflated Poisson model that we can run. And there's actually a couple of different flavors of that, but a zero-inflated model is probably something that we'd want to consider. So before we do that, let's just turn to a histogram of our outcome in order to determine whether or not we have an excess of zeros here. And though we did find with the model that we fit that the predictors seem to do a good job of describing the distribution of elephant mating, the Poisson regression may not necessarily be a good fit because we have such a large number of zeros. Now, again, just because we have a large number of zeros doesn't necessarily mean that we're going to have over-dispersion, right? Because as we increase our value of x, if the conditional mean increases as the conditional variance increases, then it shouldn't be a problem, right? But this is a cause for many instances in which you will have over-dispersion. And so we're going to run this test, and we're going to try fitting a zero-inflated Poisson regression. So first, to run the test, we have already loaded in the background our AER library, and we're using the function dispersion test with our Poisson model object. Now, from this, we can see that it doesn't actually seem to be like the null hypothesis test here has actually generated a test statistic that would surprise us under the null hypothesis, which is that there is no over-dispersion. And we can see here that actually the estimated dispersion parameter, so that lambda, is about 1.1, which is not really troublesome, because our alternate hypothesis is that the true dispersion rate is greater than 1. So we cannot reject the null hypothesis that it is greater than 1 given the estimated parameter of 1.1. So from this dispersion test, it doesn't really seem like we need the zero-inflated Poisson model, but just for pedagogical purposes, we're going to walk through how to do it anyway. And just for some general intuition as to what is actually happening when we run a zero-inflated Poisson, in terms of fitting the model, we're actually combining two data generating processes, first of which is just modeling a zero or anything else, and that's a logistic regression model. And then for the something else, the ones that have a non-zero count, then we're running a Poisson regression model. So with this zero-inflated Poisson model, we need to model the probability of being a perfect zero. That's going to be the logistic regression. And then we're going to model the Poisson part, the count, with a Poisson regression. These are two different generalized linear models that we're using to work together to try to explain these potentially two different data generating processes. Now, we can do this zip model in R quite easily using the PSCL package and using the ZERO-INFLATED function. This works in the exact same way syntactically that we would write our code using the LM or GLM function, where we have our outcome as the number of mates and our covariate is going to be age in years. So what we get back is, again, estimated coefficients for both parts of this data generating process. First, we have the zero part, the logit, which you can see for the zero model. And then we have the Poisson regression, so the count. And from this, we can see that there's really further evidence that we may not need the zero-inflated model because there doesn't seem to be a reliable association between age and whether or not someone just has a mate, right? It does seem as if the process is the older an elephant gets, the more likely they should be to have a larger number of mates. So we may have actually chosen the correct model in this case. Now, as kind of a pleasant reminder here before we end this module, I just want to end by noting that count data often has some sort of exposure variable. And by this I mean it indicates the number of times the event could have happened, right? So you can think about a count out of a number of potential successes. And if we did have that information, we could incorporate that into the Poisson model using the offset option. Now, just to wrap up, in this module, we talked about how to estimate as well as interpret our Poisson regression. We talked about how Poisson regression connects to the other types of generalized linear models that we've been talking about. And more importantly, we even talked about instances in which the assumption of conditional mean and conditional variance being equal, when we may want to actually incorporate two different types of GLMs, the Poisson and a logit, into a zero-inflated Poisson.